Have you ever wondered about the area of a shape trapped inside a circle? Imagine 4 points on a circle's edge, forming a quadrilateral. Just how much space is contained inside? Over 1300 years ago, an Indian mathematician named Brahmagupta found a surprisingly elegant answer. Here is his beautiful result. The area of this cyclic quadrilateral, with sides A, B, C, and D, equals the square root of a very symmetrical product, S minus A times S minus B times S minus C times S minus D. Here, S is simply half the perimeter. A really good way to deeply understand math is to play with it yourself. Before we break down the proof, I encourage you to pause the video here. See if you can find the area using just a single diagonal line and a bit of trigonometry. Don't worry, I'll wait. Alright, let's build the intuition together. Consider our quadrilateral, inscribed perfectly in the circle. Let's label the side lengths, A, B, C, and D, and now, let's draw a diagonal across it. Notice how this single line beautifully splits our complex shape into two simple triangles. The area of the entire shape is just the sum of the areas of these two triangles. If you recall that the area of a triangle is 1/2 times the product of two adjacent sides and the side of the angle between them, our total area is just 1/2 AB sine B, plus 1/2 CD sine D. Now, here is the crucial, almost magical property of a cyclic quadrilateral. The opposite angles always add up to exactly 180 degrees. Because of this, the sine of angle D is exactly equal to the sine of angle B. And remarkably, their cosines are exact opposites. Because the sines are the same, we can factor them out to simplify our expression. The total area becomes 1/2 times sine B, multiplied by the quantity AB plus CD. Let's keep this equation tucked away for a moment. If we square both sides, we get this expression. But notice, we still have this angle B stuck inside. We really want our final formula strictly in terms of the side lengths. To eliminate the angle, we can turn to the law of cosines. Applying the law of cosines to both triangles sharing our diagonal, we get these two equations. Remember how the cosines were exact opposites? We can use that fact to rewrite the second equation entirely in terms of cosine B. Now, we have two different ways to describe the square of that diagonal. If we set them equal to each other, a bit of algebraic restructuring allows us to isolate cosine B perfectly in terms of just the four side lengths. Let's bring back our old friend, Pythagoras. Since sine squared is simply 1 minus cosine squared, we can substitute our massive fraction in, turning it into one large, albeit intimidating, algebraic expression for the sine squared. It looks messy, I know. But look closely at the numerator. That's a classic difference of squares. This means we can factor it into two much cleaner, more manageable pieces. Let's focus on the first piece. After rearranging the terms, it collapses beautifully into a pair of perfect squares. And if we substitute in the semi-perimeter S, this factor simplifies all the way down to a very neat expression involving S, C, and D. We can run the exact same trick on the second piece, collapsing it down. And suddenly, through the dust of all that algebra, a gorgeous symmetry emerges. The entire numerator factors into 16 times 4 nearly identical pieces, S minus A, S minus B, S minus C, and S minus D. Let's substitute this back into our original area equation. You can see almost everything beautifully cancels out, leaving us with area squared equaling simply the product of those four terms. Take the square root, and there it is. Brahmagupta's stunningly elegant formula, proven completely from geometric fundamentals. But wait, there's a really lovely, hidden consequence to this. Watch what happens if we take one of the side lengths, say D, and slowly shrink it all the way down to 0. Our shape is no longer a quadrilateral, it's a triangle. And the formula naturally simplifies directly into Heron's formula. Brahmagupta's theorem is actually just the grand generalization of Heron's formula. What's most incredible is that Brahmagupta published this in India over a millennium before European mathematicians independently arrived at similar results. a true testament to the profound depth of ancient mathematics. If you enjoyed this proof and visualization, smash the like button, drop a comment below, and subscribe for more. Next time, we'll explore a beautiful puzzle about points in a plane.